Hello everyone, my name is Dhayalan Shakthivel. I'm a researcher at the Bendable Electronics and Sensing Technologies Group at the University of Glasgow. In this presentation, I'll be presenting our work titled Using Machine Learning to Predict the Statistical Distribution of Metal Nanoparticles using a dewetting process. This slide gives an outline of the presentation where I start with a general introduction of machine learning and its utility in nanofabrication. And then I'll be briefly highlighting about what's the significance of metal nanoparticles, especially in the context of fabricating flexible sensors and as well as using them for applications in flexible electronics. Then I'll be briefly discussing about what are the various fabrication techniques which has been used in the literature for the fabrication of metal nanoparticles. And then I'll be explaining at the end, towards the end, I'll be explaining about the dewetting process, which has been discussed largely in the current work, and what's the advantage of, what is the key merits of using that process for producing nanoparticles. And then I'll be explaining about the experimental data we have been obtained for gold nanoparticle dewetted gold nanoparticle, from which the data has been created to develop a model to predict the statistical distribution of the nanoparticles. And then I'll be concluding the presentation with showing the upcoming directions based on the current or developed model towards a broader applications. Recently, machine learning has been used in many different applications or technologies, starting from robotics, image recognition, and pattern recognition, or using identification of pattern using a large amount of data. So extending that machine learning, the state-of-the-art machine learning algorithms or the training models towards nanoscale, nanofabrication for the development of new devices and for many applications and flexible electronics is one of the crucial factor in the upcoming era. For many optimization processes which are carrying out in nanofabrication, either we are developing a particular kind of a stack for a given application. So, for example, if we're developing a new three-phase stack for development of any optoelectronic devices, or you're developing a new material system for the fabrication of a novel device, for example, if you want to develop a neuromorphic field effect transistor, we need to carry out multiple runs to get optimized recipe, either in the material development, or we need to carry out a lot of electrical and mechanical characterization to qualify the device for a particular application. Machine learning enables researchers to analyze a large data sets by training models that can be used to classify the observations into discrete groups. Basically, what it gives into two different aspects. One, it will help us to decide what is the, suppose we are developing a new material, what is the metrics of performance, which could be decided using analyzing a large data sets. Or if you don't know what's the natural outcome of a new optimization recipe, this machine learning techniques will help us to predict on the outcome of the. And largely, the machine learning tools has been used even many fields which is not involved intensive data, but in our case of nanofabrication, it creates a plenty amount of data which has been not used for the subsequent new developments. So machine learning, in a way, we can say that it's reshaping how researchers really collect and analyze and interpret the data. So nanofabrication has the potential to benefit by using the machine learning algorithms, either to develop a new hardware or develop a new recipe, or we want to test in a hypothesis whether this process will work for the particular device or not. So many unknowns in the nanofabrication process, which is available when you're developing a new recipe. So these ambiguities could be solved by using this machine learning algorithms. For example, Electron microscopy is one of the powerful tool which has been used in nanoscience or nanotechnology research in various aspects, either material development, device development, or such, or any circuit development or development of a new novel integrated circuits. All the steps we are using electron microscopy. But the microscopic data which we are generating in the process, which has not been used potentially for the subsequent process. So this work, the current work, is one of the kind of a prototype which is showing that how we can really explore the possibility or exploit the uh, um, machine learning tools to reduce the number of optimal runs required for any optimization, or we how to use the data which we are generating as part of the nano materials or fabrication research. So coming back to the metal nanoparticle, where we are trying to apply the machine learning tools to characterize a pattern of nanoparticle developed using this process. So nanoparticle has very good implications, very good important applications in flexible sensors and flexible devices. For example, if you, very highly sensitive touch sensors has been shown using metal nanoparticles, where the conductivity of deposited on a flexible substrate has been very sensitive to touch and or any mechanical deformation, which has been which has been shown to be applicable for development of electronic skin. Or if you're using any flexible chemiresistor, which needed to sense gaseous species of harmful, toxic or flammable gases in the order of sub uh, parts per million scale, which could be detected using metal nanoparticles. This example, if the functionalized metal nanoparticle deposited on a substrate over a small strain variation in the structure, which could lead to a significant change in conductivity, which could really used to produce the change in resistivity could be directly correlated with the absorbed gas over the functionalized metal nanoparticles. Indirectly, this metal nanoparticle could be used for other applications such as nanowires fabrication. Nanowires, one of the key building blocks for the fabrication of flexible field effect transistors, where the metal nanoparticle has been used as a catalyst particle to produce nanowires, because the dimension of the nanowires, diameter of the nanowire is decided by the metal nanoparticles. So likewise, we are able to, there have been many demonstrations which has been shown the nanoparticle could be used for flexible sensors, or it has a very good applications, optical sensors and catalysis, which has been used to in the larger context, which has been used to produce flexible panels, electronic skin, and wearable and health systems. And this slide briefly explains about what are all the important techniques which has been classified techniques used to produce metal nanoparticles. And generally, the classification comes from two major classification, either top down and bottom up, where the top down method uses a starting bulk material which has been chopped into a small nanoparticle using a chemical or physical etching process, which is used to produce the nanoparticles. And the bottom up uses a chemical reagents which has been used to grow the crystals of a predefined of a required size using a controlled chemical reaction. So many like chemical reduction, hydrothermal, photothermal, which has been used to produce this nanoparticle, variety of nanoparticles, as well as in physical techniques, alloying, mechanical alloying using ball milling techniques, or any other vapor phase techniques such as laser ablation and vapor deposition techniques has been used. But dewetting is a unique technique where it doesn't fall either as a bottom up or top down. It doesn't use etching or growth technique, where a simple any vapor phase technique could be used to produce a thin film of metal, which is heated to high temperature, and then it breaks a small droplet. So the process in a straightforward way, it looks very simple, but it's very sensitive to the experimental conditions. So this has honed a very good advantages compared to the many other different techniques. So this slide explains what are all the important what are the experimental steps involved in the producing nanoparticle. So we are forming a continuous thin film and heating at high temperature, and then because of the temperature and stress related effects, the film is break into small droplets. So these are all the important experimental parameters like thickness, temperature, and how long we are annealing it, and heating rate are playing important role. among this thing, the thickness and temperature, the film initial thickness and the temperature play a crucial role to determine the final particle size. So the main advantage of this technique is whatever the size we are producing, it's all single crystalline. That's one of the key advantage. And using this technique, we are able to produce wide size distribution. We want to produce sub 10 nanometer, be able to produce as well as micron sized particles. And this technique allows to help us to allow us to produce nanoparticle over large areal coverage, and it's the nanoparticles are really produced in a very high density, and it's a compared to any other technique, it's very simple and cost effective. So this slide explains briefly about how what I mentioned previously. These particles are various sized, changing from sub 10 nanometer to 100 nanometer range and 1 micron range. But if you are going to reduce the particle size, the statistical distribution and the density are in a very controlled way. As we are going to increase the particle size to over 100 or 200 nanometer, over 100 nanometer, the statistical distribution varies. So this nanoparticle produced using at temperature 900 degrees centigrade and at duration of 30 minutes and hydrogen ambient, which is not required for gold nanoparticle, and at a pressure of atmospheric pressure condition. So as I said, thickness and the temperature are one of the crucial factor. So for the current purpose of to develop a model, we have taken a gold nanoparticle from a thickness of 1 to 4 nanometer, which we have varied, and we are able to produce a wide particle size distribution from sub 10 nanometer, sub 50 nanometer, sub 100, sub 150, and sub 200 nanometer particles, which we are able to produce. So the crucial factor is on an average, on an average, the process is able to produce 10 power 20 particles per centimeter square. That's the scale we are arriving it out. So if you want to measure, so that's a if you view in terms of the microscopic, if you convert that into data, we are having a huge amount of data, but which doesn't fitted into any model which could be used to further produce any other different material. So the aim of the work is to show what are the pathways which we can use to formulate to using this microscopic imaging, and that could be produced to give a data, and how we're using the data to produce the models, and that model could be will explain us about the distribution, and the model could be used to train the further processes. So we are used in that work, we are used a Gaussian and Gamma function based fits or models, which have been used to fit nanoparticles of 3 different size regions of 50, around 70, and around 150 nanometer of particle sizes. And the reason behind we have been used, the distribution is a Gaussian distribution or a normal distribution, we can see, where there is a minimum and maximum and a peak. And we want to understand what is the density of the peak, so that suppose somebody want to produce a nanoparticle of 100 nanometer, they want to know what's the thickness, what's the temperature they want to use, and how long they want to hold the annealing, and what's the particle size they'll be resulting. So these factors, we want to identify these factors without performing an experiment. So this model, if they take the model and train some of the few of these experimental data which has been produced for different materials, they'll be able to predict what experimental conditions they need to use to predict the model. So using the Gaussian and Gamma function, we have found that both are the mean absolute error between these models are almost same. I think both the models are fitting, but compared to the Gamma, I think the Gaussian function has a better mean absolute error. So for this purpose, we are recommending that we are suggesting that the Gaussian based model will be a classifier will be beneficial to understand the process. And in conclusion, in conclusion, we are able to produce a huge amount of data using a microscopic classification of the images, and which could be used a Gaussian classifier. And using this model, we'll be able to train and to understand the influence of each of the experimental parameters as we used in this dewetting process. I'd like to thank our funding agency, EPSRC, and the Royal Society and European Commission for our research funding agencies. And I'd like to thank my team members for supporting um, for all the collaborations, for all the internal collaborations. And I'd like to thank for listening to the talk, and I'm happy to take any questions. Thank you so much.